Computing an injective or one-to-one mapping from a triangle mesh to the 2D plane is a fundamental task in graphics and geometry processing. A map is called locally injective if no triangles are degenerate, neighboring triangles have the same orientation, and the total angle around each vertex is 2 pi, that is, no overwound vertices. Further, a map is globally injective if there are no overlapping triangles. In practice, we also need to avoid entirely inverted maps. Some applications require mappings under positional constraints, such as constraint texture mapping and handle-based deformation. Given a set of positional constraints, our goal is to compute a globally injective and inversion-free map. Existing methods for injective mapping are not designed for arbitrary positional constraints. The classical method, Tat embedding, can guarantee injectivity but needs to fix a convex boundary and doesn't support positional constraints. Maintenance-based methods need injective maps to initialize, which are not generally available when there are positional constraints. Inversion-free methods focus on removing inverted triangles, however, they cannot avoid overlapping between triangles. We propose, to the best of our knowledge, the first method for recovering a globally injective map from an initial non-injective map under positional constraints. Our key contribution is a novel energy that promotes global injectivity with theoretical guarantees. We first introduce an energy that captures the non-injectivity of a map. Given a mesh and a boundary, we consider the difference between the total unsigned triangle area and a novel quantity that we introduced called occupancy. The occupancy is the total area of the plane where the Van number with respect to the boundary curve is positive. This difference, which we call the excess area, captures both the total area of inverted triangles and the overlapping area between triangles. Unfortunately, the excess area is not suitable for optimization because both the unsigned area and the occupancy are not smooth. For example, as the triangle moves out of an inverted state, the unsigned area is not smooth when the triangle becomes degenerate. To smooth it, we use an energy we introduced in last year's SIGGRAPH called the total lifted content. The energy is controlled by a non-negative parameter alpha, and it becomes smoother as alpha increases. On the other hand, the occupancy is not smooth when the map transitions out of an overlapping state, and the sharp change happens when two boundary edges coincide. To smooth it, we replace each edge with a circular arc, whose center angle is theta, which is a constant parameter for every arc. We define the arc occupancy as the difference between the occupancy of the new curve formed by these arcs and the total area bounded by each edge and its arc. Here, the theta angle also controls the smoothness of the energy. As the theta increases, the energy gets smoother. We show that the resulting smooth energy, which we refer to as the smooth excess area, or SEA, enjoys several theoretical properties. First, SEA is an upper bound for both the total overlapping triangle areas and the total areas of inverted triangles. That is, it captures the non-injectivity of a map. Second, and more importantly, the global minima of SEA are guaranteed to be locally injective, and its overlapping area can be made arbitrarily small for sufficiently small alpha and theta. Although this theoretical guarantee only concerns the global minima, we find that minimizing the energy using an off-the-shelf quasi-Newton solver is quite successful in practice. We evaluate our method on a novel benchmark for constraint parameterization. The benchmark contains over 1,000 initial non-injective maps with positional constraints. Compared with two state-of-art methods for removing inverted triangles, our method shows a significantly higher success rate in recovering maps that are inversion-free, locally injective, or globally injective. Here's an example from the benchmark. The initial map has a large area of overlaps. Our method is able to find a globally injective map within 1500 iterations. The zoom-in shows that the boundary does not touch. However, existing inversion-free methods are unable to resolve the majority of triangle overlaps. We end with an example from the benchmark where our method failed to recover injectivity after reaching a maximum number of solver iterations. This configuration, which we call the crossing arm, involves two parts of the shape crossing over each other. Minimizing our energy shrinks the overlapping region, thus slowing down the progress. Resolving this and other failure modes would be an interesting direction for future research, and so is the extension of our energy to 3D maps.